Washington Data Science Seminar. As part of the University of Washington, we acknowledge the Coast Salish peoples of this land, the land which touches the shared waters of all tribes and bands within the Suquamish, Tulalip, and Muckleshoot nations. Today, our speaker is Dr. Fangfang Yao, who is going to present about mapping human and climate alterations to lake water storage at the global scale using statistical learning techniques. Dr. Fangfang Yao is a postdoc fellow in the Cooperative Institute for Research in Environmental Sciences, also known as CIRES, at University of Colorado Boulder. He holds a Ph.D. in physical geography from Kansas State University, and also has a master's in Geographic Information Systems from the University of the Chinese Academy of Sciences. His primary research explores the interaction among lakes, climate change, and human activities. Now I would like to invite Dr. Yao to begin his presentation at our seminar today. Thank you.
Yeah, thank you so much, Nicoletta and Dave, for the introduction and for the invite. I'm so glad to be here. Is everyone hear me okay?
Yes, we can hear you great. Thank you.
Okay, yeah. Thanks for that confirmation, Dave. So in today's talk, I want to talk about our recent progress on understanding the decadal variability in global lake water storage using satellite data and modeling. So before I get started, I would like to acknowledge to my collaborators on this work, Dr. Sven Nibler, Rajraj Goplan, Dr. Jida Wang, Zinfranco Guito, Dr. Yoshihida Hida, Dr. Yoshihida Wada, and Maria Bird Nguyen, and Dr. Lincoln Pitcher. So why we focus on lakes? This map shows the global distribution of natural lake and reservoirs. According to the Hydrolink Global Database, there are 1.4 million natural and man-made water bodies across the globe, larger than 10 hectares. These water bodies provide accessible resources of water and food, create recreational activities for human beings, as well as provide many essential ecosystem services. And in total, they cover about 3% of the global land surface and storing about 1.88 thousand cubic kilometers, which is equivalent to 475,000 billion gallons, which is the largest amount of the surface water storage, accessible surface water storage on Earth. And over 95% of the global lake water storage is stored in large lakes, lakes larger than 100 square kilometers. And for your reference, an area of 100 square kilometer is slightly larger than the area of Lake Washington. And many of the large lakes has been acknowledged as an important source of water and renewable energy, that is hydropower, as well as Ramsar sites of the national importance of wetlands. But recent study indicate there are some of the largest lakes was drying dramatically, including the largest US lake, Lake Mead, and the Great Salt Lake, the largest one in the Western United States, and the Lake Ermia in Iran, as well as the largest freshwater body, Lake Poyang in China. And perhaps the most devastating case is the Irish Sea. This set of MODIS imagery shows the sea was drying pretty consistently over the last decades. And in 2014, the area of RC is only about 5% of its previous extent in 1960. The desiccation for the large water bodies can cause several consequences threatening the human water food security, as well as environmental degradation. So for example, the exposed lake bed, salt lake bed from the Salton Sea is threatening the human health because it becomes new dust storm, and as well as threatening the surrounding croplands. And a recent study from Nature indicate during the past 3 decades, approximately 90,000 cubic square kilometers of permanent water area was lost, an area equivalent to the Lake Superior. And at the same time, 108,000 square kilometers of new water bodies was formed elsewhere, meaning new reservoirs. This pattern signifies a substantial shift in lake water storage. And another study, also from Nature, indicated the substantial change in terrestrial water storage. The dry region were getting drier and the wet is getting wetter in terrestrial water storage, indicating substantial shift in hydro climate, which also potentially affected lake water storage. But our knowledge about the lake volume change at global scale, even for large water bodies, is pretty limited. And for example, existing studies only documented the lake volume change for dozens of large lakes across the globe. But given there are a couple of thousand large water bodies larger than 100 square kilometers, the vast majority of large lakes do not have a volume record. And we know even less about the drivers behind the lake water storage change over the recent decades, except for a few regions. For example, on the Tibetan Plateau, existing studies indicated the recent increase in lake water storage on the plateau was primarily attributed to the widening trend in hydroclimate. But existing studies on attribution of lake volume change do not always agree with each other. So for example, the dominant driver of the desiccation of the largest freshwater lake in China, Lake Poyang, was in debate. Some studies indicate the drying was primarily caused by human activities. For example, the regulating of 3 gorge dams and for human water use. But other studies indicated the lake water loss was primarily caused by the climate variability associated with ENSO signals. So to address these gaps, we aim to advance understanding of recent lake water storage change at a global scale, mainly on larger lakes, by answering the following 2 questions. The first one is, how has lake water storage changed over the past 3 decades? And second, how can recent lake water storage change be attributed to climate change, climate variability, and human activities? And I will divide the following slide based on these 2 questions into 2 parts. The first one focuses on the quantification for lake volume change from supply data. And the second one focuses on the attribution of the observed change. I would like to touch some bases for estimating lake water storage. These 2 figures shows conceptual diagram of the concept. So in order to estimate lake volume change, we need to know the hypothermic curve, which is the function between lake area and the lake level. Once we got this hypothermic curve, we can use it to be combined with either lake area or lake level to deduce the storage change. And the hypothermic curve can be derived from the bathymetry data or high resolution DEM. But unfortunately, neither the bathymetry data or the high resolution DEM was available, freely available at the global scale. But we still have the opportunity to calibrate the hyperthermal curve based on the coherent observation of lake area and lake level from satellites. And here I show an example of the largest inland lake water body, Caspian Sea. So we can use satellite imagery to construct the time series of lake area for this sea, and then use the satellite radar altimetry to derive the water area of the sea. The radar altimetry provide lake level observation can be back to the 1992. It was originally designed to monitoring the sea level, but can also be used for observe the water level of very large lake. And once we got the coherent observation of lake level from altimetry and the lake area from satellite imagery, we were able to calibrate the hyperthermal curve, for example, as a polynomial function. And then we combine the hyperthermal metric curve with monthly lake level to deduce the monthly lake volume change, as shown in the lower right panel. But there is one limitation for radar altimetry. Is its coarse resolution and large inter-track spacing, which means the majority for larger lakes do not have the level coverage from radar altimetry. So we need to turn alternative options. And one good option is from the recently launched ICET-2 satellite from NASA, launched in 2018. The ICET-2 provide a very accurate observation of the land surface because it is a LiDAR laser altimetry, can provide a very high resolution to detect water bodies across the globe. As you can see here, the black dots indicate the cloud points from the LiDAR measurements, and the rectangular flat area is the lake surface, and showing for the Crater Lake in Oregon. And using ICET-2, we were able to estimate the water level for water body as small as 4 hectares, which of course we can use it to cover the water level for all larger lakes larger than 100 square kilometers that without the water levels from radar altimetry. As you can see, because the ICET-2 satellite is recently launched, we were able to derive the water level from 2008 to the present. Because of the inconsistent temporal coverage of water level dataset, we need to construct a consistent time series of lake areas in order to deduce the lake volume change spanning the past 3 decades. And we choose to use the Landsat satellite, including Landsat 5, Landsat 7 and 8, because Landsats provide pretty high resolution at 30-meter resolution, covering the global land surface. And also it has a long temporal coverage spanning multiple decades. But there is one issue with the Landsat imagery. The cloud cover, because it is an optical sensor. So if the cloud blocks the view of the satellite, the object underneath the cloud cannot be viewed from the satellite on that date. In order to incorporate as much imagery as possible, because if we estimate lake volume, lake area time series at an infrequent frequency, which could cause a bias in estimating the long-term trend, because lakes are highly sensitive to climate and human alterations and show dynamics as signal to interannual time scales. In order to incorporate more imagery, including those from contaminated cloudy imagery, we developed a new algorithm to estimate lake area from those imageries. The rationale is that for Atlantic water body, the shoreline for its lake water extent can be treated as an isobus. A smaller water extent should be constrained, contained by a larger lake water extent associated with a larger, higher isobus. So for contaminated imagery, even though a water body may be partially observed, as shown in the upper right panel, if we have a higher and a lower isobus extracted from cloud-free imagery, the complete area of this partial observation can be constrained. So if the higher and the lower isobus are quite close to each other, we can simply use a linear interpolation to estimate the complete area of the partially observed water body. And details of this algorithm can be found in our recently published paper in Human Sensing of the Environment. So by incorporating the cloud-free and cloudy imageries, we were able to derive a long-term time series of lake area at a pretty high resolution, temporal frequency, for example, close to monthly. The blue dots indicate the areas extracted from the cloud-free imagery, and the red dot indicates the area from contaminated imagery. So as you can see, by incorporating this recovered area from cloudy imagery, we were able to improve the temporal frequency by more than 50%. And as you can see, the combined time series reveal highly detailed information about the interannual and seasonal changes in lake area. And we leveraged 3 decades of Landsat observations for lake area time series, combined with level measurement from satellite altimetry, both from radar and LiDAR sensors. We were able to deduce the lake water stability change across the globe. And here shows the dots shows the locations for our of the lakes in our database. In total, we compared nearly 2,000 large lakes across the globe. And based on this global database, we estimate the trend in lake water storage over the past 3 decades. As shown in this map, we identify widespread decline in global lake water storage over the past 28 years. And 2/3 of large lakes showing a drying trend. The lake water storage loss progress along the major global regions, including the Western Central Asia, the Middle East, the Western India, Eastern China, Northern and Eastern Europe, Oceania, the US, the Northern Canada, and South Africa, and the majority of South America. So our finding suggests the drying trend global-wide are more extensive than previously thought. If you remember in the introduction slide, a recent study indicate the dry region were getting drier, the humid region were getting wetter based on 14-year observation from grid satellite. We confirmed the dry is getting drier, but we also reversed substantial decline in lake water storage across the humid regions, including the high latitudes and the wet tropicals. So our next question is trying to answer what caused the widespread decline in lake water storage, or generally what's the driver of recent change in lake water storage across the globe. So in order to do so, I would like to introduce the hydrological cycle, which is a pretty simple concept. So the moisture transport bring precipitation, and then precipitation bring water infiltrate into the soil and the ground, as well as generating the surface runoff flowing into the lake and the ocean. and the water return to the atmosphere through evaporation and transpiration from vegetations. Or the hydrological flux and the stocks can affect the lake water storage. I would like to highlight the human alteration for the lake water storage. It can affect lake water storage through climate change. For example, the anthropogenic warming increasing the evaporative loss from the lake surface. It can also affect lake volume change more directly. For example, the damming and for water use, which can reduce the inflow to the lake. And in addition to the anthropogenic factors, the lake water bodies is also modulated by climate variabilities. For example, the precipitation and the lateralized flow. So we can use a function for precipitation, river discharge, potential evapotranspiration, temperature, human water use, and groundwater to model the change in lake water storage. And here we use multiple data set to construct an ensemble of regression model to model the lake volume change. We use 4 precipitation product, 1 naturalized flow product, 2 potential evapotranspiration product, 3 temporary product, and 4 human water use product. And to construct the ensemble for 96 regression model for each lake. We also use the BIC criteria for each regression model to avoid the overfitting because BIC has a penalty on adding new variables. So for example, if 2 variables, P and Q, are highly correlated, only 1 will be ended up in the final regression model. And then we also note that for the groundwater, we do not have the global data set to quantify the groundwater at the global scale. So we will not be able to incorporate groundwater storage into the regression model. But based on existing studies, the groundwater impact on decadal variability on lake volume are pretty limited. And we also acknowledge that for reservoirs, they are highly regulated, except particularly for sizable ones, as we do not have the knowledge about how humans regulate reservoir at the global scale. So we only apply this regression framework on natural lakes. And using the ensemble for regression model, the dominant driver for lake volume change for each lake is determined by the popular vote. So each candidate can one vote if it can explain the most variance in lake volume in each regression model. So we simply count the dominant driver from each regression model and use the popular vote to assign the dominant driver of the lake volume change to that predictor, and in this case, precipitation. Because our goal is to attribute the lake water storage change to climate change, climate variability, and the direct human activities, we further group these 5 predictors into 3 categories. So if the lake water change was dominated by precipitation or naturalized flow, we assign the change to natural variability. And if the change is modulated by temperature or potential evapotranspiration, we assign the change to climate change. And likewise, we assign the change to human water use if human water use can explain, won the popular vote. And the agreement for the ensemble model on the attribution of lake volume change is pretty high. As you can see from this map, The light green dot indicates the agreement below 50%. The dark green does denote the agreement higher than 75%. And here is our results for the global attribution for lake water loss. And in total, the volume of drying lakes declined at the rate of 93 gigaton per year. This rate is equivalent to the water mass for the largest lake. That's the reservoirs in US, Lake Mead, which means the Lake Mead, the water mass equivalent to Lake Mead is gone every year from these drying lakes over the past 3 decades. As you can see from this map, the human-induced change is evident. For example, in the high altitude regions and the dry land, most of the lakes are attributed to the either climate change or direct human impact. And human impact also account for, the dominant driver for some of the largest lake water loss. So, for example, the desiccation for the Aral Sea in Central Asia, the Dead Sea in the Middle East, the Salton Sea in California, as well as the Lake Mashquita in Argentina was attributed to direct human activities. And whereas the climate change further caused the drying of the lake Tashika in Egypt and Godariza in Afghanistan, the lake, these 2 lakes was completely dried during our study period. And beyond this hotspot, the lake water study change was attributed to the natural variability, including the Caspian Sea, Great Salt Lake in the west, the Lake Ermia, the Lake Titicaca in South America. And we noticed that another study attributed to the Lake Ermia to the human activities rather than the climate variability. And we take a close look at our regression model. It indicated that the explanation power for human water use and the climate variability are comparable, although the climate variability explained a little bit more compared with human activities. And thus, it is we noted that it could be a possibility for the drying of the lakes. This lake is a combined factor of the drying climate and human water use. So in addition to the lake water loss, we also revealed the lake water storage increase in regions elsewhere. But these lake water storage increase are more constrained in space. So, for example, they are mainly located in some remote regions, including the interior Tibetan Plateau, the northern Great Plains in North America, as well as the Great Rift Valley in Eastern Africa, because they are spatially constrained, and these regions are located in relatively remote regions. The increased water storage may not necessarily benefit large populations. And we note that the drivers for this increased lake water storage is largely attributed to the natural variability, which is not quite surprisingly, because this is consistent with existing findings. For example, as we treated earlier, the lake water storage increase in the Tibetan Plateau was attributed to the hydroclimate wetting trend, which is also confirmed in this study. And the northern Great Plain in North America is also revealed, from existing study. the precipitation over recent decades was increasing in this region, as well as recent recovery from droughts from the Eastern Africa contributed to the recent rise in lake water storage in some of the largest lakes in this region. So the takeaway from this talk, we were widespread decline in lake water storage over the past three decades. And most of the large lakes were drying in both arid and humid regions, which indicate the substantial drying trend across the globe. And also extend our knowledge of, the drying trend is not only occurred in arid regions, but also in humid regions. This could have very important implications for the water cycle. So for example, there is one theory under the warming condition, the water cycle could be intensified, which could increase the increase in precipitation over land, particularly for the humid regions. But we do not observe the increased lake water storage, surface water storage in humid region, at least over the past 3 decades. And we perceive there could be at least 2 potential mechanisms for the decline rather than increasing trend in lake water storage. For example, existing studies revealed a global increase in land evaporation, which means the increasing precipitation may partition more into the ET rather than the surface runoff. And also another possibility is because the longer recovery time of droughts across the globe. So for example, in Amazon, the drought in 2005 hit this region hardly. It also followed by another major drought in 2010, which prevents the recovery of surface water storage from droughts. And secondly, we identified substantial impact of the human activities and climate change on global lake water loss. As you can see, a lot of spot, the lake water loss were actually dominated by the human-induced factors rather than the natural variability, which indicate the recovery of these lakes needs substantial maximum effort, otherwise would be impossible under a warming condition. And thus, our studies underscore the urgent need of incorporate the sustainable water use as well as climate change adaptation into future surface water resources management. And because of the timing, I cannot include too much into this talk, but I would like to talk about very briefly some of my ongoing and planned project, which include documenting volume change in medium and small size lakes. So this talk, I mainly talked about the study change in large lakes across the globe. As I mentioned earlier, the ISAT-2 satellite was able to provide the water level measurement for lakes as small as 4 hectares. The satellite imagery can definitely observe the areas of lake area for water bodies at this size. So it is absolutely possible to deduce the volume change in smaller lakes and to further extend the coverage of our global database. And are also currently working on a global lake database for small dams, because the large dams are well documented, but small dams are less documented and often missed in existing document registry. So our effort currently using some hydrological evidence combined with satellite observation from water body area time series to kind of compare a new global database of small dams. We also targeted attribute tracking the change in lake water quality in addition to water quantity, because water quality also matters, especially for sizable water body. The impact could be as equally important as those the drying trend in lake quantity. And we have a few ongoing proposals with some federal agencies, including understanding impact of climate isolation, such as the ANSO, the PDO, on large lakes, and the reconstruction, the paleo lake level during the Holocene, as well as assessing the socioeconomical and the environmental impact of dams in the threatened Brazilian papa in South Brazil. And here is the list of the reference of the talk as I used for your interest. And lastly, I would like to thank again for my collaborators for their extended support for this work. My collaborator, Dr. Ben Nibler, Dr. Razif Goplan, Dr. Inkem Beecher from Boulder and CIRES, and Dr. Jida Wang from Kansas State University, Dr. Jim-Francois Gretal, and Dr. Maria Merge Nguyen from French Speech Agency KINAS, and Dr. Yoshida Wada from International Institute for Applied System Analysis, YASA, in Austria. And I acknowledge this research is funded by the NAWA Cooperative Agreement with CIRES. And with that, I would be happy to take any questions. Thank you.
Fangfang. For our friends on Zoom, please use the Q&A button in the bottom corner to post your questions. We can take some from the room. I'll actually get started, Fangfang. I'm aware that the Landsats changed over time. I'm not a satellite person, but I think 4 and 5 were identical copies, but 7 and 8 had substantial improvements in resolution. How did that impact? Did that play any role in your study? How did you reconcile the fact that there were different resolutions for the imaging that you were getting out?
Yeah, thanks, Dave. That was a great question. So the sensor difference, can affect the reflectance that we used for detect the surface water to separate water from the land. But for our case, I did not include too much about the details of water delineation. More details can be found in this paper. But in generally, we use the kind of the water indices, normalized water indices, as well as other water indices to kind of highlight the contrast between the water and the land. So for example, the normalized difference water indice, NDWI, for example, is a difference between the reflectance in the near infrared band and green band. So the absolute difference from these sensors can be minimized due to this normalization. But I do agree, maybe the major concern about the Landsat 5 to the Landsat 7 and 8 is the coverage. As we know, the Landsat 5, if you go back to the 1980s and maybe early 1990s, the coverage for Landsat 5 is not truly global. So this is why we do not extend our study period to 1994. The 1994 Landsat 5 already provide the 30-meter observation at that time, but because of the temporal coverage, we will not be able to do so. And also, because the Landsat 5, the coverage is kind of limited, we have more. You can see from the lake time series in the upper panel, we have more area recovered from contaminated imagery compared with the area from good quality imageries, which signify the need for incorporating more contaminated imagery into our consistent time series construction of the lake areas.
Awesome, thank you very much. We have a question.
Hi, thanks, great work. This slide here is actually my question. It shows several sequential estimations that are based on corrupted data. And I'm wondering how corrupted is too corrupted to use, and how much error does that introduce to your estimates?
Yeah, so we did a accurate assessment of the lake area estimated from contaminated imagery, and we found that the imagery with contamination up to the 50% within the lake ROI can be used, and the accuracy for the recovered lake area for imagery within this degree of contamination is about 2.2%. You can check more into our RC paper for details.
Oh, okay. Great questions. Like great minds think alike. Any other questions from the audience? Anything on Zoom, Nicoletta? Oh yeah, please.
I'm curious about the tools you use and computing you use to handle this massive data set. If you could elaborate a little bit on this, that would be awesome. Thank you.
Yeah, thank you, Dana. This is a good question. So we used a couple hundreds thousand imagery for this analysis, which definitely extensive computation workload. And we implement our algorithm on a cloud platform from Google's engine, using Google's infrastructure on cloud computation to enable delineation of this product. And even though with the cloud computation from Google, it still takes us several months to complete the monthly time series spanning 3 decades for nearly 2,000 large lakes across the globe. Yeah, but you're absolutely right. This work would be impossible without cloud computation.
That's a ballpark estimate of how many terabytes of image data you're working with?
I'm not quite sure about this, but yeah, the short answer is, simply to convert the 200,000 Landsat imagery and plus, the size of each Landsat scene could cost. Yeah, but I do not have the exact number at this moment.
I think the technical term for that is a ton of data. Okay. What's that? This is your metric ton, right? We should be SI.
Hi. So for the changes attributed to human activities, did you find any surprise, and the changes? Is there any changes that is actually not well documented elsewhere, and then this is something new? I imagine maybe you can find something in country with no good data, or in war, or in the other, I don't know, yeah.
Yeah, this is a very good question. Yeah, you're right. So we do find the human alteration of lake water storage. So as you can see here, this is kind of the most severe human impact, because the human impact need to be dominant to be selected as the dominant driver showing in the map here, right? Which means for example, if lake water storage was partially attributed to the human water use or climate change, so this will not be shown. So this is roughly conservative estimate of the human alteration of decadal variability of lake water storage across the globe. And to answer your question, we do confirm the dedication of arid sea and dead sea from existing literature, which are already suggested so. And we do have a few insight in addition to that. For example, the certain sea in California, although there are some possibility of it can be influenced by the human activity, but has not been confirmed, which being demonstrated in our study. And the other lake in the Argentina, the Lake Chiquita, is also attributed to the human activity, which means human contributed at least more than half of the lake water loss. And yeah, these are the major new insights. And we do find that there are some common patterns for the human driven lake water storage loss. They are located in generally located in the basins with a drying climate, which indicate when less precipitation supply from the nature, and human tend to withdraw more water from rivers, which lead to the destination desiccation of the terminal lakes.
Great, thank you. We have time for one more question.
Is there like a database with geographical coordinates of all the lakes, or are lakes identified by some type of classification algorithm?
You mean which database I use to identify the larger lakes across the globe, right?
Yeah.
Yeah. So I use the Hydrolink Database. I think this is the freely available database. You can download it from their website. And in the very beginning, should be here. So you can see it's pretty documented. Yeah, a lot of lakes, millions of lakes across the globe, and I simply use the threshold 100 square kilometers to identify all large lakes across the globe.
Right. So if like, do changes ever happen to this database? Like, are new lakes ever added, or like?
Yeah, this is an excellent question. So I do not think the natural lake has been added a lot, because most of them are well documented. But the reservoirs has been added a lot. So this database includes probably 700 of reservoirs, which is absolutely undocumented. And there are some existing studies that compared the georeferenced locations of the dams of reservoirs. And one of our work currently in review with Earth Science Data also can be, the preprint can be available online, and the database also released is the GEODA, the GEOD dam A and R reservoir database. You can check out that. So you documented about 20,000 reservoirs, which is more extensive than reservoir documented by Hydrolink Database.
Thanks.
Thank you very much. I'm afraid that probably what happens is lakes disappear from that database because they dry up. Would that be a fair thing to say?
Yeah. Actually, that could be true. So especially some very shallow saline water bodies can be dry out. A lot of lakes we identified has been in this database, for example, in Oceania, in the central area of Oceania, a lot of very large lakes larger than 500 kilometers simply dry out, or simply, only appear for a very fraction of the time throughout the year. Yeah, they can be dry out over time. And there are one of our recent proposal with NSF is to want to investigate the drying lakes during the Paleo period, the Holocene, in the northwestern India, the Indus civilization regions. So the large lakes previously stand the civilization, but nowadays this region is a desert. The lake is gone.
All right. Well, thank you very much, Dr. Yao. We'll have one more round of applause from our audience.
Yeah, thanks so much for having me, Dave and Nicola.
Thank you very much. And this concludes the formal portion of our presentation today. Have a great day.
Yeah, you too. Bye.